Welcome to solverfy.
Okay, this problem's a little tricky. So we have a spherical black body with a radius of 7.5 centimeters and a diffraction grating with 3,850 lines per centimeter. We're given some distance away, we create an interference pattern with its first bright about 14.4 degrees from the central axis. And given only this information, we're asked to find the temperature of this black body. And with a little bit of additional information, say that this black body's radiating 12 megajoules of energy, we are asked for the time it would take for it to radiate this energy. So at the onset, it may not be clear how we would approach this problem. So we have to actually pull some equations from wave theory of light, some interference, some slit interference equation. You might remember this one, which relates where m is the index for the mth bright fringe, lambda is the wavelength of light, d is the slit distance rather, and theta is our angle to the mth bright fringe. So we will need this to actually relate our diffraction grating to this light. And we also can use the empirical fact that the temperature times the peak spectral wavelength of our emission spectrum is equal to this constant. We will also can use the fact that the energy emitted is proportional to the fourth in its temperature, and of course area in this constant, sigma. And of course the fact that energy is related to power by delta T. So some constants we'll need. We have most of them. The only constant that wasn't explicitly mentioned is the sigma constant. Which is 5.67 times 10 to the negative 8 watts over meter squared kelvins to the fourth. So this is everything we'll need. Let's jump into it, start us off. Okay, so to start, we can use the fact that the first bright is 14.4 degrees from the central axis, and the lines per centimeter to find d and m and theta. So we actually have everything we need to find the wavelength of our light, assuming that this wavelength is going to be the brightest in the spectrum emitted by this black body. So thus, we should say, for the first bright, it's the case that m equals 1. So d sine theta is simply equal to lambda. And d, simply 1 over the number of lines per distance, 385,000 lines per meter. Lines is in a proper unit, an SI unit, so we'll simply get meters. The sine of 14.4 degrees to the first max, which will give us a result of 6.4 times 10 to the negative 7 meters. And this is the wavelength of our light. Once we have this wavelength of light, we can actually start calculating. It becomes much more clear what to do from here. So using the fact that T lambda m is equal to a constant value, 2.9 times 10 to the negative 3 meters Kelvin, we can then find the temperature by dividing. 2.93 times 10 to the negative 3 all over 6.4 times 10 to the negative 7 meters, which is our wavelength. You see the meters cancel out in the units, and we're left with temperature in Kelvin. So our temperature will end up being 4,531 Kelvin. So this is something quite hot. Okay, and that's the first thing we're asked to solve, so that's the main result. Now, assuming that our black body has this temperature, and it's an ideal black body, meaning we have a Planck distribution, if we know the total energy emitted by this black body, we can express that as a power times a delta T. We can express a power as an intensity times an area times a delta T. We know the area of this black body because it's spherical and we have its radius. We can then express the intensity of our radiation as sigma A, or as sigma T to the fourth times A times delta T. And finally, we can express our area in terms of our radius. So you have sigma T to the fourth, pi r squared, 4 pi r squared, I should say. This is a sphere. The area of a sphere is 4 pi r squared. Delta T. Thus, delta T is simply the total energy divided by all of this stuff. Sigma T to the 4 pi r squared. Great. So now we can plug in T, R, and E, and of course the constants, and we will get a result of 7.1 seconds. So that's it. Really think through the process for the problem. The hardest part is finding the wavelength of the light given this interference pattern. From there, it becomes much more simple. Okay, thank you very much.